Okay, 10th grade, here we are with lesson number 4, Bond Enthalpy. So hopefully this will help kind of clarify and cement your understanding of bond enthalpy, just enthalpy of reactions in general, because we're going to take it from the big picture of the whole reaction to breaking it down to individual bonds between individual atoms and molecules and compounds. So here's your template for today. Make sure you have a space for a diagram here for bond enthalpy. I'm going to go over energy diagrams just to be really clear you everyone understands how to use those. We'll look at some average bond enthalpies and do some practice calculations. We're going to do 3 together, and then there's 2 multi-part questions that will be your homework to complete. Okay, so first things first, what is bond enthalpy? So we worked with reaction enthalpy already last lesson. Can you define the term enthalpy? So enthalpy is the heat energy of a reaction. So bond enthalpy is the heat energy of the chemical bond. And it's the sum of those bond enthalpies, those bond energies, those 2 terms are synonymous, that determines the total reaction energy, total reaction enthalpy. Again, energy enthalpy in this case mean the same thing. Better to use the word enthalpy, but you'll find a lot of resources online will talk about bond energy. So I'm going to use both of them just to make sure you guys are able to use all the resources available to you. Okay, so it's the sum of the difference between the energy to break bonds and energy to make bonds. So making a bond takes energy, and breaking a bond releases energy. So if we think about the law of conservation of energy, we know that these 2 quantities have to be equal. So here's a really good diagram here. This one I want you to draw. We have diatomic hydrogen, 2 hydrogen atoms bonded together, the covalent bond. If I break that bond, that requires 436 kilojoules of energy to break those 2 apart. And then if I have 2 hydrogen bonds and I want to make them into a diatomic hydrogen like this, that's going to take energy, but exactly the same amount that it took that was originally broken is how much it takes to make it. So if ever you want to know how much energy it takes to make something, if you can find how much energy it takes to break it apart, then you can figure that out from there. It's exactly the same but opposite signs, right? So this is negative 436 taking in 436. So taking it in, plus 436 and negative 436 for releasing it. They have to be equal and opposite because of conservation of energy. Energy cannot be created or destroyed. So since chemical reaction is just making and breaking bonds, you break it into its simplest idea, then we can use bond enthalpy to determine delta H. And it really is, delta H really is just all the bond enthalpies broken down and added together again. So we need energy to break bonds. Energy is released when bonds are being formed. The total energy is the difference between the energy needed to break a bond and the energy needed to make the new bonds. So it's the difference between the energy used and the energy needed. So the energy needed and the energy produced, the way to say it. Okay, and that's the difference to tell you if your reaction is endothermic or exothermic, how much the total energy of the reaction is, delta H. So how do we connect this to exothermic and endothermic reactions? Take a minute and think about this. So in an exothermic reaction, my delta H is going to be less than 0. It's going to be negative because I'm going to be losing energy, which means I'm going to do what with my bonds? Are my bonds more or less energy? Which part's which? Take a minute and think about this. So the energy to break the bonds is going to be less. The energy to break the bonds is going to be less the energy to make the new bonds. So I'm releasing more energy for breaking bonds than I'm using to make a new bond. That's exothermic. So endothermic means I'm pulling in energy. So to make the new bonds, it's going to have to take more energy than I have available from breaking the bond. So making the bonds needs more energy than I have available from just breaking those earlier bonds in my reactants. Okay, so an exothermic reaction, delta H is negative because the bonds are formed to require less energy than the bonds which are broken. And in an endothermic reaction, delta H is positive, of course, because the bonds formed need more energy than bonds which are broken. So we've seen these 2 diagrams before. I really like them because they summarize the system with exothermic and endothermic, and if you didn't draw them before, make sure you include these now because they're really good diagrams to help connect all those ideas together. So we saw this before. I want to kind of come back to this. Before we talked about enthalpy of reaction was the reactants compared to the products, the balance between them. So we have bond energy here, positive bond energy being released from the reactants, so we break those bonds, and negative bond energy being used to make the products, right? And if this is larger, then it's exothermic, and this is larger, it's going to be endothermic. So just coming back to this diagram again, you should already have it, I don't need to draw it or anything, but just kind of remember how this all fits into the reaction as a whole. Okay, so let's go to energy diagrams. We've seen these a bunch of times, so I want to take a minute and just be really explicit and make sure everybody really understands what all the different parts of these are. So in last class, we looked at exothermic and endothermic energy diagrams, and we'll look at that slide again in a second. But you need to connect this to bond enthalpy, not just overall reaction enthalpy. So often we see these the curve line. So in this particular one here, I have a flat line for my reactants, a flat line for my products, no curve line here. And I'm showing this is showing the enthalpy of the bond enthalpy here. So I have the sum of the average bond enthalpies of the reactants. So here's my reactants. I have ethene and I have hydrogen gas, and my product is ethane. And here's my reaction happening up here. Okay, this is two flat lines, so just focusing on the delta H, just focusing on the energy being used here in the enthalpy. It's not focusing on the kind of reaction progress. So the curved line we often see is because chemical reactions often aren't just a single reaction. Like this is here summarizing the reaction being shown in this diagram is being shown here. Okay, so we have ethene plus hydrogen gas in the presence of a catalyst of nickel at 150 degrees Celsius will then become ethane. Okay, but this process, and like many other chemical reactions, needs many kind of small steps. It's not an instantaneous change. So the curved more accurately represents that whole process and talks about the activation energy in a more kind of visual way. So while we sometimes see them as just flat lines, reactants, products, or reactants and products higher, oftentimes you see them like this. And you already drew these from last class, so don't draw them again. But you'll notice here we have my reactants, products, and we're showing the curve of the reaction sort of starting to progress and happening, hit my activation energy, and it started to happen really quickly, and then I'm producing a lot more products. And my energy change here from my reactants energy level to my product energy level. Of course, it's exothermic because delta H is negative. And here are my reactants and my products. Reactants are lower, products are higher, so I'm endothermic. They have more energy in the products. And again, I have an activation energy. It's going to go down. We're going to talk more about energy and reaction rates during the next lesson. Again, we already saw this. I just want to connect all these ideas together for you. Okay, so how do we know this information? Well, we talked about experimental procedures last class for how we can calculate the delta H for reactions in styrofoam cups and calorimeters, measure the change of heat of water based on the energy produced by a reaction to figure out how much energy is being used or produced in a chemical reaction. But today we're talking more theoretical. We're using the bond enthalpies that have been predetermined. So these are the average bond enthalpies, and these have been calculated meticulously by many, many, many chemists in many, many labs, and they calculate them many, many times with very precise equipment, and they take the average of all these different kinds of bonds. Now, look at this. What kind of bonds do you notice have the most energy, and why do you think that's the case, or the most enthalpy? Well, the multiple bonds definitely are slightly higher than the single bonds. And the biggest ones here we have is carbon triple bonded to oxygen, which is possible but is beyond your understanding of chemistry right now to understand why, so I'm not going to bother trying to explain it. And then we have, as they have less complicated bonds, we have carbon and triple bond to nitrogen. That's 891 kilojoules per mole. Okay, carbon triple bonded to the carbon, 839 kilojoules per mole, really high in the triple bonds, double triple bonds over here. Single bonds are a lot less, and some of them are quite low, like diatomic fluorine, 155 kilojoules per mole, really low. What else is another really low one here? 163 for a nitrogen single bond. 151 for diatomic iodine. Notice how the low ones are the same atom itself, they're diatomic. Okay, and the less electrons are being shared in those bonds, or being, yeah, these are all covalent bonds, they're all being shared, then the less energy it takes to break them. The more electrons being shared, the stronger the bond, the more energy there's going to be. So think back to your understanding of covalent and ionic bonding back from beginning of this year, back from grade 9 chemistry, middle school chemistry, those kinds of bonds where ionic bonds take a lot less energy, and they have a lot less energy. So ionic bonds have more energy than covalent bonds. The covalents are sharing electrons, and ionic bonds have an attraction. Okay. Now the reason why these are averages is not because they did like 500 trials and took the average. They're getting the same value. The problem is that the bonds actually have different amounts of energy based on the situation they're in. So, for example, a molecule of methane, CH4, greenhouse gas, 1 carbon, 4 hydrogens, all bonded to the same carbon. You would think that every single carbon-hydrogen bond in that methane would have the same amount of energy in that bond. It's actually not true. The first bond to break is the most difficult. It has the most energy, and the more bonds you break after that, the less energy they require. Other things that affect this as well. For example, there's other molecules surrounding a compound that can maybe help reinforce those attractions or polarity that can also cause it to have more energy to break that bond than before. So that's why these are an average. Okay. Now you would never be expected to memorize these numbers. You need to understand them, the patterns in them, and how to use them. But they will always be given to you. Either in the question itself, they'll give you the ones that are relevant, or they'll give you a table like this one to refer to for a set of questions. I recommend you put the table in your notes, or take digital notes, or make a note that you'll have to look at it, be given it in your practice questions. Okay, so this is a practice question. So here we're going to do 3 together, and then you'll have 2 that are going to be homework to do. So here's example number 1. The question is, find the energy change in the following reaction using the bond energies given. So here's the bond energies that they're given to you. You don't have to figure them out. Here's my reaction. I'm going to explain why the reaction is exothermic or endothermic using bond energies. So I look at my bonds here, my reactants. These are the bonds that are broken. I have 4 carbon-hydrogen bonds. Here's methane. 4 of those, so I have 4 times 412 kilojoules for every carbon-hydrogen bond. I have 2 oxygen double bonds. So oxygen to oxygen is 400, so that's actually an O, not a C, guys. Oxygen to oxygen, 496, so 2 of those is 496. So I add up the total of this, I get 2,640 kilojoules of energy in my bonds that are being broken. That's the energy being released as I break those bonds, and the reactants part of my reaction. And the products. Okay, my carbon-oxygen bonds are 743 kilojoules, and I have 2 of these. 1, 2. So times that by 2. My oxygen-hydrogen bonds, here we go, 463 kilojoules. I have 1, 2, 3, 4 of those, because there's 2 waters here being produced. So that's 4 times 463, 3,338. So energy change is energy needed to break bonds minus energy released making bonds. So 2,640 minus 3,338 gives me negative 698 kilojoules. So this is exothermic because more energy is released making bonds than is needed to break the bonds. So if you get mixed up with a negative, positive, exothermic, endothermic, you can always look here. Am I releasing, do I have more energy to make bonds or to break bonds? Okay, because I'm releasing energy making bonds, more of that energy is being used releasing than to making bonds than to break bonds. It's exothermic. Okay, so here if I have my the reaction diagram to kind of look at this as well, another example, where I have my reactants, I have my products, I have the energy here, and here's kind of separating them into individual atoms, and they're going to be rearranged into these ones here. Okay, just to kind of connect the energy graph curve here. Okay, so here's 2 more practice questions. I want you to try them for yourself. So pause the video, try these 2 for yourself. We'll go over the answers after. Okay, so example number 2, you have to find the energy change. The following reaction using Bond energy. So here's my reaction. I have hydrogen gas plus oxygen gives water. And is it exothermic or endothermic? So I have 2 of the hydrogen-hydrogen bonds. So it's 2 times 436. I have 1 oxygen-oxygen bond, 496. My total is 1368 kilojoules. I have 4 oxygen-hydrogen bonds, 2 in each water, for a total of 4. 4 times 463, I have 1852 kilojoules, bonds being made. So energy to break, minus energy being made, 368 minus 52, I have minus 484. This is exothermic, again, because the more energy is being released, making bonds, that energy is needed to break bonds. Okay, number 3, if I try this one. So I have here an alcohol, I'm going to decompose it, decomposition reaction here, and I'm going to exothermic endothermic. So hopefully you figured this out, check your work. We had 5 carbon-hydrogen bonds, we had 1 carbon-carbon bond, 1 carbon-oxygen bond, and 1 oxygen-hydrogen bond. Here's my total. I had bonds being made. I had 4 carbon-hydrogen bonds, 1 carbon-carbon double bond, 2 oxygen-hydrogen bonds, and my total. I subtract them, and I have plus 45 kilojoules. So it's endothermic because it's more energy needed to break the bonds than to make the bonds. Okay, here's your practice questions. So number 4, number 5, these are practice for you to do, and we're not going to go over them. They are going to be homework. So you have to write the equation for this reaction with hydrogen gas burning in oxygen. The only product is water. It's exothermic. Explain what that means. Draw the energy profile and figure out the overall energy change using the bond energy or bond enthalpy. And here I have 4 reactions, and here's my table of bond energies. Okay, so calculate the energy change and why are they exothermic or endothermic. We are also done now with big idea number 2. Big number 2 is how can models be used to demonstrate energy changes in a chemical reaction. So think about models here of the energy graphs that we've been using. Even chemical reactions are also models, things that can help us understand the energy in a chemical reaction. Okay, so your homework is to upload your notes to today's lesson, including the 2 sets of practice problems and your big ideas page. You should have the first 2 both done at this point. Your final exam is based on big ideas, so make sure you do a good job with those. Okay guys, we will go over stuff on our Zoom on this Friday. If you have any questions in the meantime, feel free to reach out to me. We can do little mini Zooms and check in and help you understand what you have to do. Take care and stay safe.